So now we can go into understanding how we can actually apply these things into any types of like long divisions. So long division concepts. So now that we understand our rules, multiples of tens, dividing by zeros, dividing by ones, we can look at examples of dividing even more kinds of numbers. So our goal is, again, to allow you guys to understand the steps that we are using. So we're going to be doing this by actually starting off with a concrete example and kind of walking step by step what this would look like using the algorithms that we have, or the algorithm that I'm going to teach you. So an example is, if there are 2,868 pennies, so 2,868 pennies, and you want to split them equally into 12 different piles, basically, how many pennies are going to be there per pile? So how many pennies per pile? So mathematically, if we're going to be representing this, it would be the same thing as saying 2,868 divided by 12. Now we're going to be using the same kind of like distributive property that we talked about in multiplication, and we're going to be basically grouping them into groups of tens. So what you could do is, looking at this big crazy number, we can start off by saying, like, how many times can this number 12 go into a number like 2868, okay? Now, if you know your 12s tables, then you know that 12 times 1 is 12, and then 12 times 2 is 24, and then 12 times 3 is 36. Now, obviously 12 is too small to go into, like, let's say these first two numbers, 28. And 36 is way too large to go into this number, like 28. So 24 is our, like, very simplest thing that we could do. It's like the best option that we have available. So if we do 12 divided by 2868, the method by us actually doing this might seem a little bit different. So you guys might already be like aware of, whenever we divide, we look at how many times does 12 go into 28. But this time, what we're going to be saying is, like, 12 goes into 28 200, or 2 times, right? So we're going to put 2 here. So that becomes 24. But this is the opposite of kind of like the distributive property that we did in multiplication, because instead of just focusing on like our ones values, we're going to go all the way into like the largest value that we can have. So in this case, it's thousands, right? Because this is like 2,868. So we'll be adding basically 2 more zeros at the end. And the reason why will make more sense. So if we're going to add 2 more zeros here, we have to add 2 more zeros here at the top. And so we're basically going to have, as a result, if you subtract both sides, 2868 minus 2400 as 468, okay? Now, the next step that we want to do is, how many times can 12 go into 46? Well, we don't want to worry about it going into like the 400s or whatever. So again, let's just look at our 12s table. That's the same thing as basically saying 12 times 1 equals 12. No, 12 times 2 equals 24. 12 times 3 equals 36, and 12 times 4, now we get 48. So 48 is way bigger than this 46 that we have. So instead, what we're going to do is just be focusing in on the 36 here. So that's basically 36 here. So again, we want to go all the way. We're not just going to be focusing on these two parts. So we'll go all the way to 360. So that gets us the value of 30. So now, as you can see, we're not adding everything like straight up. If you know like the traditional way of dividing, we're not just making it like 23 and like going on from there. We're actually stacking it, which is very similar for how we kind of did with the multiplication method. So now when we do this, this basically gets us at the bottom of 108. Actually, I'm going to clear this so that we have more space. So again, if we're going to have our 12 divided by our 28, actually that's still more space. 12 divided by our 2868, we already decided that we have our 200s available to get us 2400. And then we already decided we have our 30 available to get us our 360. Now if we subtract this from here, all we're left with is 108. Okay, and now this 108, how many times can 12 go into this? So again, I'll just have my 12 tables on the side. And so this gets us 12, this gets us 24, 36, 48, 60, and 72. So what we're trying to do here is, again, we're only looking in terms of like multiple of 10s. We want like these really kind of easy numbers to work with. And so the way that the solution actually works is that it only focuses in on the 60. And the reason why, you might be thinking like 72 can even go like that. And even if you go farther, you have like your 84. And even farther, you have like your 96. And so all of these would still fit within this constant of 108. But we focus in on this 5 because, as we'll see, when we add in this 5 over here, we're just left with 48. And this gets us to like a nice clean number, which goes back to this kind of 4 that we have available to us. So now we can add in a 4 at the top. And when we add all of these together, our 200 plus 30 plus 5 plus 4, we get our answer of 239. So this is going to be basically our answer. So again, all we're basically doing is separating our pennies into more and more piles. So if we go back into the actual like concrete example, when we're looking at this, we can start by putting the 2,868 pennies into 200 pennies per pile. Okay, when we do that, 200 pennies per pile, we are left with 468, right? 468 left, that's not in any kind of pile. Then again, we're going to put 30 more pennies into each pile. So this is going to be 30 pennies per pile. Then we are left with 108 pennies. So then we're going to say 5 pennies per pile. And we're finally left with 48 pennies. So we're finally going to just do 4 pennies per pile. And these groupings that we have, these 200, 30, 5, 4, if we add all of that together, that gets us our answer of 239. So if you want to look at this in terms of multiplication, you can again see this as the same thing as saying 12 times 239 equals our 2868. And when you separate out 239, we're multiplying it by 200 plus 30 plus 9. And this is kind of like what we were representing with our equation as a whole. Because like this 9 could have also been represented as like 9 times 12. So this is like what our 108 is. The solution separates it into 5 and 4, but if you know like your 12's tables, then this actually kind of makes more sense. And this is exactly what we did just now with our division. So I'm going to take a little break here. I want to see, oh yeah, someone asked, are we going to get to do practice problems? Yes, we are going to be going over practice problems. And somebody else asked, what if it was 1205 times 105? Okay, they said actually never mind for that. But yeah, 1205 times 105. Basically, this is how we're doing it. The same kind of steps. We're doing the division, but now we're just doing the same kind of multiplication problem, but in terms of the division form. So still same distributive property. So any questions now? If you get this all, thumbs up. If not, then like text me individually, and then we can go over like any questions that you have. So I got 1 thumbs up, 2 thumbs up. Okay, so I'm assuming this is good. Again, we will be going over practice problems, so we can again go over the kind of steps that are needed for this. Okay, so this is just kind of like a short note on why we don't use the non-traditional algorithms. So again, you guys might already be used to doing division like in a certain way, like you might have already been taught in school or your parents already showed you, and that's completely fine, like whatever way works best for you. But the reason why we focus on these kinds of problems is allows for more efficient understanding of the actual algorithms and the actual math that's behind this, and less about kind of like rote, robotic kind of notation. Otherwise, what we'd be kind of reverting back into is not looking at it in terms of like groupings of 10s or 100s, but instead looking at it in terms of like individual parts, which might make it more confusing. So the steps that we showed should make it more intuitive. Like the math is not hidden. We're taking out equal groups and keeping track of like the total groups that are made. So some strategies that you guys can like implement whenever you're dealing with these kinds of problems in the first place is to always look for ways to compute division efficiently without ever having to actually even use this division algorithm at all. So for example, if we're going to divide anything by 4, we know that anything times 4 is the same thing as dividing by 2 twice, right? So if we had 100 divided by 4, that's the same thing as saying 100 divided by 2, and then taking that answer and dividing it again by 2. So 100 divided by 2 is 50, divided by 2 again is 25. And that's what 100 divided by 4 is. So if you relate these kind of concepts together, you don't necessarily need to even know what the fours table is if you already understand that 2 is always halves, 4 is a quarter, and a quarter is just a half of a half. Additionally, you can also, again, like just split the quotients into parts that are easily like divisible. So another example is if we were to have 6,000 or 63,042 marbles, if you want to split them into like 7 buckets equally, again, we'd be focusing on the kind of parts that make sense to us. We know that 63 is divisible by 7 because 7 divided by 63 is 9. And we have, again, like our 3 extra zeros, so we just carry over our zeros. On the other hand, we have 42, so 42 divided by 7 is just going to get us 6. So if our answer as a whole is just going to be 9,006. So you don't have to worry about actually even breaking it down to the steps like how we did before, like saying 63,000 and dividing it by 7 like that way. If you even can look at it conceptually, or 63,042. If you think about it even conceptually, understanding what these kind of parts equal, then again, you can just like add them all together. So I'm just gonna like quickly go over kind of the divisibility rules for some simple numbers. So let's say that we have 2, 5, 10, 100, 4, and 25. So we already kind of discussed 10 and 100. We already know that anytime you have like multiple zeros at the end, you can always just cancel out those zeros. So 90 and then 900 versus like 80 and 800. You can just focus on these first values, the 9s and the 8s, whenever you're dividing by anything. And then always carry over the zeros at the end. Always cancel the zeros at the end. Again, we just talked about like the difference between 2 and 4. 2 is always having something together, while 4 is always a half of a half or a quarter. So whenever you're dividing anything by 4, just divide it by 2 twice, and you basically get the same answer. The last two are kind of like neat tricks that I know of. So for 5, whenever you're dividing anything by 5, or even multiplying anything by 5, a neat trick is to know that even numbers. So like let's say, I want to explain this. If you have like 13 times 5 versus 12 times 5, the best way to answer these kinds of problems, you don't even need to know the 5's table. It's just remember that 12 divided by 2 is 6. So you're just going to add a 0 at the end. So it becomes 60. 13 divided by 2 would get you 6.5 because 13 isn't an even number. So you could just do 6.5 times 10, which is just 65. And this rule works for basically any number. So 9 times 5 versus 8 times 5. 8 divided by 2 is 4, so your answer is 40. Versus 9 divided by 2 is 4.5, so that gets you 45. And even really big, crazy numbers. Like let's say, okay, not that big and crazy, but yeah, let's say 26 versus 27. 26 times 5 is the same thing as 26 divided by 2, which gets you like your 130. And then 27 divided by 5, or times 5, so 27 divided by 2, they get you 13.5, so you get 135. And this same kind of rule you can like flip on its head whenever you're dealing with like divisibility. So if you ever have like 130 divided by 5, you can kind of think about what numbers would get you like 13, or what numbers would like if you do 13 times 2, well that's just going to be 260. So your answer originally was just 26. So this is some kind of like neat mental math tricks. If you having trouble with this, let me know. I can go over them again. But this is just something that might help you whenever you have like a lot of bigger numbers that have 5 in it. You can just remember what that is. And then finally with 25, it's just always going to be like variations of 25, 50, 75, and 100. So it just keeps on repeating this. So after 100, again, you get 125, 150, 175, 200. And then you get 225, 250, 275, 300. So if you realize that this kind of like pattern exists whenever you multiply by this 25, then you understand kind of what the answer would be no matter what times you go 25, either in terms of like multiplication and divisibility, or even whenever you're dividing like 300 by 25. You can kind of see intuitively that pattern that occurs. So then these are the divisibility rules. These are the strategies that you guys can use, and this is what we're going to be using for the actual practice problems.